at Drexel University in Philadelphia, Pennsylvania, and is the co-founder and chairman of the Leatherback Trust, a nonprofit organization established in 2000, focused on protecting the nesting beaches of the endangered leatherback sea turtle, the largest sea turtle species in the world. His research and conservation efforts have paved the way for several eager scientists and passionate conservationists, such as myself. Dr. Spatilla has mentored students from all over the world, including Argentina, China, Costa Rica, Greece, and the Netherlands, just to name a few. Among Dr. Spatilla's most notable achievements is that he was the first to document temperature-dependent sex determination in sea turtles. On a personal note, I would like to say a few words about how our paths first crossed. I had the pleasure of getting to know Jim as a graduate student at Drexel University, where I was studying the population dynamics of diamondback terrapins. Leading volunteers on citizen science expeditions through the salt marshes of Barnegat Bay as a member of the Earthwatch Institute research team. Jim and I spent time preparing fish for terrapin traps and repairing fyke nets, among other tasks. This is when I learned to listen to his words carefully, as he would oftentimes infuse humor into conversation, sometimes when you would least expect it. For those who spoke English as their second language, sometimes this was lost in translation. But I grew to really appreciate this about Jim. During one of our lab meetings, I recall Jim describing the value of earning your PhD, reminding the students of the PH, describing the degree we were working so hard to earn as one that would help us to learn how to think, problem solve, and relate to fellow humans as we pursued careers in science. He encouraged us to pause and consider why we were doing what we were doing and question the approaches of other scientists, even if their name was Jim Spatilla. I carry these words with me every day. Thank you, Jim, for your mentorship, steadfast support, and willingness to make a separate trip all the way down here to Charleston to share your knowledge and experiences with us. We greatly appreciate it. Dr. Spatilla's scientific achievements mark the tip of the iceberg, as he is a person of great depth and perception. It is truly an honor to host him at the College of Charleston today. I could go literally on for hours. Dr. Spatilla means the world to me, and I'm very glad that he's with us. So I'm just going to switch gears just momentarily to introduce the other distinguished scientists I mentioned in the beginning. So Dr. Dave Owens is an emeritus professor in the biology department here at the College of Charleston and remains actively engaged with the local scientific community. In addition to his effective and down-to-earth approach to mentorship, Dr. Owens is known for his work in reproductive biology in both sea turtles and diamondback terrapins. Among his many notable achievements, Dr. Owens is a Fulbright Fellow, recently spending a year in Myanmar, sharing his vast knowledge of sea turtles and marine conservation with students. So now that I've introduced Dr. Spatilla and Dr. Owens, I would like to give the floor to Dr. Owens for a few additional words about his experiences working with Dr. Spatilla. So please join me in welcoming Dr. Owens first. Thank you.
Jim's an old friend, and I'll just make a couple more points if I could that are off these topics. In the 70s, most of my work was about hormones of turtles. And everybody poo-pooed it and said, oh, that's basic work, you don't need to do that. Jim was my inspiration because he was working on basic things like acid-base balance and equations for metabolic rates and all these kind of stuff. And I said, well, he can do it. And he actually had great funding from the National Science Foundation. So I tried. Initially, I got a little bit too. But so he inspired me to do it. But we also, more than anything else, we've shared students. Georgito Ruiz, Pam Plotkin, David Rostow, Michael Coyne. Oh, they were the best of the best. So, anyway, but Jim's been very collaborative over the years. But I do want to mention one thing that I actually touched on, the Leatherbacks. This is, I really think, has been Jim's passion for almost his whole career, turtle career. Of course, he did pandas, he's done alligators, he's done fish, he's done all kinds of other, but I think the Leatherbacks is where he has the best feeling for a very, very unusual animal. So I won't say any more, but Jim, thanks for coming.
Well, it is indeed a pleasure to be here to speak to you because I'm invited by Ashley in connection with Dave. And what's particularly nice today, of course, is that get to hear all these eulogies while I'm still alive. It's a positive thing. So I've been around for a while. I don't know if I've been around as long as Dr. Owens. Maybe. And what I want to talk about today is about global warming and sea turtles from a personal perspective. Now, if you'll notice here, the Time magazine cover from 2006. They had a polar bear on it, but I got rid of that and I put a sea turtle on it. We should be very worried about sea turtles and global warming. And what I'm going to do in this talk is to give you sort of a history of a rise in CO2 in the atmosphere, talk about sea turtle studies I've done, so it's very personal centric. A little bit about El Nino and La Nina. You could see the situation. It's a personal journey. It certainly does not include everybody's studies or a general overview. Now, the idea of global warming is not new. It's old, from Arrhenius in 1896, when he was a physical chemist, and he's the first one who really scientifically looked at this problem. And he computed that if you doubled the CO2 in the atmosphere, that would increase temperature about 5 or 6 degrees. And CO2 at that time was about 280 parts per million. So he predicted that this would be happening. And I think I had a conversation in a bar in Birmingham a few years ago. I was sitting in a bar with a former student who was chairman of the department. He invited me down and then took me out to dinner, but we had to go to the bar first. And there were two women there who were like a producer and ran a couple of radio shows in some thing, and they were sort of right-wing radio shows. And the lady's sitting there, and I'm sitting there trying not to get in any trouble. And he says, "Oh, he's here to talk about global warming." I said, "You're trying to get me killed here." And she says, "What? You believe in global warming? Are you a Christian or something like that?" He said, I don't believe in global warming. I am a Christian. I'm a good Christian, I hope. But it has nothing to do with what I believe. And then I explained on a napkin how global warming worked. And they invited me to talk on their talk radio show the next morning, but I had to go give my seminar. But it was very interesting, the conversations that you have. You've got three things in the atmosphere. Three minor constituents of the Earth's atmosphere. You've got carbon dioxide, water vapor, and ozone. Good. And Arrhenius figured out that CO2 absorbs infrared radiation. So does water vapor. So if you increase those things in the atmosphere, you warm up the Earth. It's the basic science of it, as I explained on that napkin. And you can't argue with that, whether or not you have any religion to believe in. Without those three gases, we'd have an atmosphere like that of the moon. So we do like to have some of that in the atmosphere because it makes our planet livable. So that's the basis of what we're talking about. Now, I always like to put up acknowledgements first. I didn't do this work alone. It's funded by, I got NSF up there, Earthwatch and others. All the sea turtle work over the years. And all the people who, not all, but many who helped. So that we don't forget to thank them. Now, let me go back to the beginning of my career, because having a career that spans a long time, I lived the CO2 story and the global warming story, and I'll tell you how it happened along with what I was doing. So this is a curve that shows CO2 in Mauna Loa Hawaii on top of the volcano, so that's pretty undisturbed by local effects. And this is from the Keeling data. Keeling is the one who started recording these data. Now he was going to graduate school and he couldn't think of what to do for a project in physical chemistry. And it occurred to him, well, he could take a mass spec on top of the volcano and measure CO2 and get his degree, so that's what he did. And it was so interesting, they've been doing it ever since. So it's one of those, I guess he could have picked something else, but he picked this. So that's the level of CO2 in 1966 when I went to graduate school. The value was 320. You got to remember 320 because that got fixed in my brain as one of the facts I would always remember, that CO2, the standard value, was 320. Things to change. When I was then a postdoc in 1970, it went up a little bit. So the postdocs and myself were working with David Gates, a world famous biophysical ecologist, climatologist, physicist, and we said, Dr. Gates, it's going up. CO2 is going up, and if CO2 increases temperature, it's going to heat up the Earth. Now, being a wise professor, sort of like Dr. Owens and I are now, which are mostly, we're still standing at an ancient age, he said, it looks like a trend, but you can't be sure. Look at the variation. It varies, maybe that's wobble in the noise. If you take the low point of the high end of the curve and the high point of the low, it hasn't changed that much. But then he said something very interesting. He said, if it continues to go up, then we're going to have a problem. So I filed that away. It was 322 at the time. I started doing sea turtles in 1978 on a ship called the Alpha Helix, which was a National Science Foundation vessel that went around the world and did physiology, took physiologists around. And there was an expedition to go study green turtles. Now, I always wanted to study sea turtles. I mean, you want to study, if you're a biology major, you want to study dolphins, whales, or sea turtles. But I was never going to study a sea turtle. But I went to a seminar. I was a faculty member at Buffalo State College, and we had a faculty meeting, like a committee meeting. Faculty members here know about committee meetings. It's going to be about space or research use or something. And you're going to have a meeting, and you're going to have several of these meetings, and then nothing's going to change because the administration didn't give you any more money to do what you wanted to do. So should I do that, or should I go see Henry Prang give a seminar on the physiology of green turtles at the medical school? So I skipped the faculty meeting and went to the seminar. It was a lot more fun. And then he gave this talk and said, oh, he's going on this expedition, but they'd really like to do sea turtles in the water, but nobody could do that because everybody knew from Archie Carr's work that you can't do telemetry in the ocean. It doesn't work. So afterwards at the coffee, I said, well, Dr. Prang, actually I can do that. I can do sonic telemetry and radio telemetry. We've been doing it on alligators and sharks and stuff. And he said, oh, great, why don't you come on the expedition? Give me 2 pages. And how much money do you need? That's too good to pass up. So I said, fine. And I went home that night and called the graduate student whose committee I was on at the University of Georgia, Ed Standora, who was one of the 2 people in the country who could make such transmitters, because you had to make everything yourself in those days. And I said, Ed, would you like to go to Costa Rica and study sea turtles? He said, oh, yeah, Jim, oh, that'd be great. What do I have to do? I said, you have to make 6 of those sonic transmitters and 6 radio transmitters, and I'll take you to Costa Rica. So it's very helpful in that instance and others that most of my best ideas and techniques have come from my students. You learn more from your students sometimes than they learn from you. So that was great. Ed and I went, and we went down to the research station. This was the research station at Tortuguero. Those were the fun days when there was no electricity and you had a generator, and here we are sitting around eating. There were plenty of bananas, but not much else. And then in the lab, here's Archie Carr in the middle with the hat on. Bob Foley was my student who was there. And I'm in that picture, but you won't recognize me. And the turtle, we take a green turtle off the beach, bring it back to the lab, work at night, because that's when the turtles are out. And when Miss Junie, the cook, wasn't there because she wouldn't let us in her kitchen, that's a orange package, is a sonic transmitter, and the lines are thermistors going to different parts of the body. And then you find an old Zodiac that was washed ashore, and if you have duct tape, you repair it, and you go out to the surf, and Ed and Bob track the turtle. I'm at shore to call their families if they don't come back. And then we also tracked on the alpha helix. And what we found was that a green turtle, a cold-blooded animal, when it was swimming, look at what happened to its body temperature. That's the top line. It goes up into the 30s. It's 35 degrees C when it's swimming. So it's an endotherm, a regional endotherm. It heats up its muscles when it's swimming. And that helps it to swim faster. And then the other temperatures are in there too. So that was our first sea turtle work. And at that time, CO2 had gone up to 335. You see it's going up, but we didn't know that. And we didn't pay any attention. And nobody else paid attention either to what was going on. There were other things to do, like clean water and clean air and all that stuff that went on in the 70s. In 1980, we went back to Costa Rica because there was an idea that temperature might affect sex determination in freshwater turtles and lizards in France. Nick Mersofsky had done some of the work on freshwater turtles. And so we decided to figure out if that happened in sea turtles. Because in Florida, they had a massive conservation effort going on to take the eggs off the beaches and put them in house trailers to keep them alive. And they were air-conditioned house trailers. And they never got any females back. And they wondered about that. So what we did is went down, we made several hundred thermocouples. That's Ed Standora and Steve Morielli. Made all these thermocouples, marked the nests of the turtles, put a thermocouple in them, put screens around them so nobody dug them up like a coati or raccoon. Left it there, 50, 60 days later, dug out the eggs and hatchlings to find out what was going on. And then we decided to make, for sure, different temperatures by shading, making a hatchery and shading some of it with palm thatching to make cooler temperatures. And then you get 100 sea turtles, and you have to sacrifice, I think we sacrificed 20 from a clutch to make sure we had enough. And you can tell by histology if it's a male or a female turtle. And what we discovered was that at 28 degrees or lower, these were all male turtles, and at 30 and above, they're all females, and it was a midpoint, 29 and a half, that gave you a mixed sort of nest or clutch. So temperature did affect sex determination. That's why there were no male turtles coming back to lay eggs in Florida. So it changed a lot of the approach. Since then, it's been done for many species. I think there's some we've tried some molecular things, and the most recent work shows there may be some gene turned on and off, activated to cause that to happen. So that was interesting. When we figured out TSD, we're just up to 337. Nobody's paying attention again, still. So that was 1980. In 1990, we decided to do leatherback turtles. Frank Palladino was a former student, and he was bugging me to do leatherbacks. And we wanted to measure the metabolic rate of a leatherback turtle. The reason for that, of course, is that nobody had done it before. And it was a curiosity. And leatherback turtles, for those of you who have not been on a turtle beach, the shell length is the size of this table. A little more than that, not quite this big. It's a big animal. It's a 300 kilogram animal to 400 kilograms, typically females. So it's a big turtle. What is its metabolic rate? It goes from the tropics where it lays eggs up to Nova Scotia, where it feeds in the summer, to Alaska in the Pacific, South America down by Chile. It goes all over the place. Dives to 1,000 or 1,500 feet. It's as deep a diving as a whale. How does it do that as a cold-blooded reptile? So we decided to measure the metabolic rate and figure that out. So here we are. Ed Jalowski was a grad student at the time. You convinced the turtle to go onto a cargo net. Ed's now a professor at North Texas State, I think. Then with more students, this allows the students to participate in the research, as in do all the work. You grab it up and then you weigh it. And I would point out that that's me in the white hat actually doing something on the beach, as opposed to directing people on the beach. So you have to get the mass of the turtle. Then you need it to breathe into some kind of a bag to collect the gas. So you need a mask over the head of a turtle. So the only thing we can figure out is a 5-gallon plastic water jug. Cut the end off, stick it on the head of the turtle. With duct tape again, you can seal it. And then this, you see there, that valvey looking thing. The open end is breathing in, it's a Y valve, and it goes out and you collect a big rubber bag of turtle gas. Take it back to the lab to find out what's going on. Walk the turtle around, do it while the turtle's laying eggs, walking on the beach, covering up, go back to the lab. We still are using the same kind of lab we used before. Somebody's little hacienda. And a close-up here shows that there's a gas meter on the left. It looks like the gas meter in a house. And then an oxygen meter and a CO2 meter. CO2 meter is that rectangular shaped thing. And so you got to calibrate that. You calibrate it with room air. Okay, well, everybody knows, or you may remember, 20.9% oxygen, that's pretty easy. And 320 parts per million carbon dioxide. So we try to make this CO2 meter 0, and it won't go down below 350 something, 3.5. So we figured it was broken. Or there's two ways to do this. One way is to turn the knob and make it 320. That didn't seem quite right. So what we did instead was to write down the 350 value, figuring we'd adjust it later, measure the amount of carbon dioxide in this bag of gas. If it was 320 or 350 in the air, and it was 5% in the expired air, then you could compute the metabolic rate of the leatherback turtle. Then, since there was no internet at the time, we couldn't Google the value, we couldn't look it up, we didn't have a telephone, we couldn't call home and ask, and we didn't have a book. So we wrote it in the book, and we came back to the lab, and then we looked it up, and by golly, it was 355. So it's good to write down the actual data point and figure out what you did wrong later. So that allowed us to compute it. Here's Frank Palladino in one of our other labs. Sure enough, we measured the metabolic rate, mass-specific metabolic rate of leatherback turtles. The circles are nesting turtles. The little black dots are covering, throwing sand around. No, circles are walking, and resting turtles are on the bottom. And we computed that a leatherback turtle has enough metabolic rate, about what you expect for a reptile of that size, and fat insulation, very thick insulation, and countercurrent heat exchangers in the flippers. That's how they could stay warm in cold water. And then when they go to the tropics, they flush blood to their skin and they could cool off. So that was pretty exciting. And at that time, CO2 was around 355-ish when I was a professor at Drexel. So for some reason, it kept going up. Now, you may have seen this curve, carbon dioxide curve versus production of emissions. And those values continue to go up, so that this year it's around, it's above 410. So when I started, it was 320, and now it's 410, 411. An inexorable rise. And that Keeling curve still has the same variation it had before. CO2 goes down in the summertime in the northern hemisphere when the plants are photosynthesizing, and it goes up in the wintertime. But you will see that it continues to go up. Now, if I had remembered the calculus that I took as an undergraduate, I would curve fit that. Not remembering the calculus, I used another technique. It's called PowerPoint drawing a line.
You can see the curve, right? Well, let's fit another line. Oh, it's getting steeper. And it's getting steeper again. So I don't need an equation to tell me that we're putting more. It's going up rather rapidly, which is in many ways unfortunate. So here is a curve of the temperature of the atmosphere, land-ocean temperature index. And I put a line down here at -2 degrees, which is the temperature back in 1880, about when Arrhenius was first talking about or first wondered about CO2 and global warming. And you could see that temperature has gone up about 1 degree over that period of time. Now, one of the effects that he didn't know about was the ocean absorbing lots of carbon dioxide, most of it, at least half of it, turning it more acid and making coral dissolve, things of that sort. But there's still an obvious increase here. So what's the effect on sea turtles? That's really what we care about. We don't care about people. There are plenty of people in the world, but there are not enough sea turtles. So somebody asked me, actually, what's the goal of conservation? I think there was a talk at the sea turtle meeting. Blair Witherington gave a talk about why do conservation and whatever. My answer is, you do conservation to keep these things alive because after the apocalypse, they'll still be there when we're gone. So there's no use them going extinct along with us. All right, well, here's that El Nino, La Nina thing. The red part is when the Pacific Ocean is warm. That's El Nino, and the blue is when it's cold, La Nina. And there are more warm periods than cold. And when that comes by, it has an effect. Now, we've been studying, as Dr. Owens mentioned, leatherback turtles at Playa Grande, Costa Rica, since 1989. And the developers and others who oppose the conservation effort have pointed out that we've caused the turtles to decline because we tagged them. And so obviously they died or went away. You see there's an exponential decline in this population from 1,500 animals down to 26 and 13 the last 2 years nesting on this beach. So what in the world is going on? Well, that decline is caused by two things. Initially, the local people took all the eggs for 20 or 30 years, and most people around the world do not have a realization that if you take all the turtle eggs, there won't be any turtles in the future. I'm not sure why that is, but they don't understand. The other thing they don't understand is in Costa Rica, eating turtle eggs with your beer is macho. And we've been trying to explain to them that eating eggs is sort of a female thing. It's not going to make you more macho. And so you had that effect, and then the other effect is the massive fishing effort in the Pacific Ocean, both from local fishing in Peru and Chile and Ecuador, and the fleets from China, Japan, and Spain that basically vacuum everything up out of the Pacific Ocean, including leatherbacks. Now we're getting the Peruvians, Joana Alfaro's efforts to convince local fishermen to put them back alive or to help find out information about them. But that doesn't happen on Chinese fishing boats, for example, because they eat everything, including the fish. They'll either eat it or turn it into cat food, or they'll use it for bait or something. So I think any turtle caught in those boats is gone. So that's one effect. That's the reason there's an exponential decline, and that is what needs to be fixed. But if you look at the ups and downs in the curve, you'll see that there's a climate effect. During El Nino, there's no food for the turtles, so they don't come back to lay eggs. So you could plot this figure, if we go back. If you just plot the peaks instead of the valleys are there because of El Nino, you might get a truer value, but the decline has been inevitable. They've noticed that they're catching fewer turtles these days. So obviously, either the conservation efforts in the ocean are working, or there are just not enough turtles out there to catch. So that's the ENSO index, and it's getting warmer in the Pacific than it used to. Now, what about the eggs and hatchlings? Remember the temperature-dependent sex determination. If you are a turtle egg, you are buried down in the wet sand, and oxygen just has to diffuse from the atmosphere to the egg, and CO2 goes the other way. We discovered that on Playa Grande, there's a 3-meter tide, which actually acts like a bellows and pushes air up and pulls it down and ventilates the nest. Because the nest is down 75 centimeters under the sand. Needs to be down there, needs to be wet in order to survive. And then, of course, temperature is going to affect it. So in this case, 55 days later, all the little turtles come out together, and on our beach, on the Playa Grande beach, is 70 to 95% female turtles now. So this is where this is, the beaches in Costa Rica. Nice view of the beautiful beaches that are still there because there's a national park created in the 90s. Mario Bosa, who was the vice minister, the founder of the national parks of Costa Rica, then the vice minister, created this park through a presidential decree in 1990. In 1994, the next minister tried to eliminate it because his brother-in-law had land there and they wanted to put a big casino hotel up. So we sort of told the news media, who went to the office there and asked him why he was destroying the park. And he announced that that wasn't true, that was a bad rumor started by this communist guy from the United States, who's now banned from the parks. So I was banned from the parks until the next election when they changed the government. And if you're not banned from something once in a while, you're not really doing your job. And so in 1995, after years of our lobbying and Mario's lobbying, they made a law. Now, the other thing that happened was I got word to President Clinton about the turtles through my brother, who was his friend, and he had the National Security Council, and they had the ambassador tell the president of Costa Rica that he really liked leatherback turtles and they should make a park. And like 3 months later, the Congress made a park. So it's the value of science that explains how you get things done politically. Now, they got done because the President of the United States asked them to do it. That's a good power for conservation. And the beach in 1995 looked like this, and it still does. We've raised $5 million or so to help pay people for their land so they don't, because they can't build on it. And there have been international cases in the international courts about whether or not the government can take American properties. Yes, they can. They have to pay them. It's very complicated. So we spend a lot of our conservation money now on a lawyer who checks to make sure things are legal, find out if properties are illegal, etc., to support the park. So that's what the Leatherback Trust does. But along the way, remember I got Ed Standora's ideas and ability got us into sea turtles? Well, Beebe Santandrian from Madrid did her PhD on the beach, and she thought that we should study hatchlings. At the time, there were so many adults, we didn't want to bother. But she persisted, and so every nest gets excavated, and we find out whether the eggs hatched or not, and what stage they died in, and all that sort of thing. So that's an ongoing thing. And since then, she has created mathematical models that will predict the effect of climate change, global warming, on hatchling emergence and hatching success, hatchling emergence. And as you can see, the upper one is hatching success, which under all possible climate scenario models of increasing CO2, it goes down from 50%, which is low, but that's what leatherbacks are, down to 30%. And emergent success, 80% of the hatchlings that hatch get out. It's going to be down to 40%. So figure out the effect of 30% of the eggs of 70 eggs. So 21 eggs, and of those 21 hatchlings, 30% get out. So 6 hatchlings get out of a clutch of 65 eggs. That makes for a non-viable future for the turtles. And when you run that in a population, it basically says they're going to go extinct, no matter what else you do. So therefore, you have to, where's the sort of point where you have to put your efforts? You have to put your efforts into making sure that the eggs don't get too hot on the beach. That's really the issue. And it's no longer an issue of sex ratio, it's an issue of survival. So emergent success on the top, female output on the bottom. And as you can see, as you raise that temperature, both of those go down. But the emergent success is the tough one. Here's the model for hatching success and emergent success. You have to keep the temperatures down. Now, how do you take a 3.5 kilometer beach and control everything? You put shade cloth over it. You pick up all the nests and move them to a hatchery. Do you put shades over each nest? You water. I always thought watering the beach would be a cool idea. Just get this thing and water all the nests. We're still figuring that out. And then this is cool. George Schillinger, for his degree, did some calculations about what's climate doing to the climate in Costa Rica. So up on top, is the surface air temperature, let's say currently. You notice that it's yellow-green, it's a little cool. And then the one on the right is what it's going to be towards the end of the century. It's getting hotter. And on the bottom is precipitation. You notice that precipitation is also going down. So it's getting hotter and drier. And in Guanacaste in particular, it's going to get hot and dry. Sandy Point is in the U.S. Virgin Islands, is a success story for leatherback conservation. The numbers used to be, I don't know, 10 or 20 days, something like that. Something low like that. They did conservation for a number of years and went way up. About 15, 20 years later, they started getting more turtles. Now it's going down again. And part of the reason is they have lower survival of hatchlings. So seasonal precipitation has gone down and annual hatching success has gone down. So they have a problem of overheating as well. And Beebe did this analysis for lots of beaches. I just want to focus on these two. Playa Grande, temperatures increasing, rainfall, not so much, some. The top line, I think, is October, then November. Notice that there are no lines for December, January. It's a dry season, it doesn't rain. The only place that looks like there'll be an increase in precipitation and an improvement in conditions for leatherbacks is actually South Africa, in Maputoland. Temperatures will go up and they'll be doing pretty well there. That's the beach in South Africa, so that condition's improving. The other effect, of course, is rising sea levels. So we've saved a lot of Americans a lot of grief by not letting them build on the beach, because in a few years they'll be underwater. The beach could move, as you can see in this picture, but a lot of beaches will be lost. I mentioned the CO2 in the ocean causing acidic conditions. It causes the corals to be affected, and with hot water they die. And many species of corals and plankton are going to go extinct in this century, and that's going to cause a cascade up the food chain and affect sea turtles. This is a hawksbill turtle picture. So, what's the future with this CO2 business? You can look at the older generation, those of us who've been around for a while, who thought that we were conserving sea turtles by our studies, only to find the inexorable changes in climate overriding those effects. So we thought we were winning, and not so much. Basically, y'all have a lot of work to do. Those of you who are students now have to find better ideas, better ways to work. If you want to talk about sustainability, you've got to get your climate under control, first of all. And then, of course, you ought to worry about other things for sustainability too, from plastics. Anybody see the YouTube video of the straw and the turtle with the plastic straw in his nose? How many people saw that? I saw that. We did that. I didn't do it, of course. Nate Robinson and Pam's student, they did it. And so that's brought up the whole story of plastics. So those things you need to worry about, but climate overall, because otherwise, not only will Charleston be underwater, but things will be very unpleasant. So I'd like to thank you for your attention, and the turtles thank you for nothing, basically. Be happy to entertain any questions.
Thank you, sir, and thank you for everything you've done. So the Leatherbacks, the oldest lineage, maybe 100 plus million years on the clock. I study the gene activity of these animals, and I am always astonished at their versatility. And I just wonder if you had any instincts or ideas or just factual knowledge about what leatherbacks have already been through in 100 million years.
Well, they've been through the big extinction at the end of the Cretaceous, for sure. Temperature changes and asteroids and that kind of thing. They went from several lineages down to one, I think about that time, and since that time. They've gone through bottlenecks in the Pacific, as far as we can tell, more recently, where they may have been wiped out and then recolonized, like the Americas. The question is, well, certainly an asteroid hitting is an instantaneous event, but yeah, the turtles should move to other nesting places, right? They should move up the coast, except there's hotels and condos all over Maryland and New Jersey and whatever. So they should find new nesting places, and they should survive, theoretically. But the problem is generation time, and the problem is, are there enough animals? In the past, they didn't have to contend with all the human effects that they do now, so that's part of the problem. But yeah, you would think that some of them would survive and then repopulate. Any of the sea turtles. They show a lot of resilience. A lot of sea turtle populations rebound with protection, for example.
Presumably nothing's exploited them to such an enormous degree as human activity.
Yeah, right. I mean, the effect in the Pacific is just incredible. There are so many boats, so many nets, so many long lines. The mortality rate on our population was 22% a year on the animals that went out, if you figure when they ever came back. And that's obviously not sustainable. Other questions?
I have a question.
Yes.
First and foremost, thank you for the great presentation. Thank you for raising awareness around these critical issues. But I guess my question is more of a fundamental sort of knowledge transfer question. Like, what you just said, how do you get the sea turtle community more broadly to understand these ramifications, right? Because even here in our local community, and full disclosure, I went to South Carolina Aquarium with the Conservation Department. One of the key things we've been trying to communicate to our constituency base is basically Cape Remain Refuge, another foot of sea level rise is going to be gone. And so when you think about that being gone, the question is where are the likely suspects for the potential other areas of land district for sea turtles, in this case leatherback. Now, the unlikely suspect is Hilton Head, but the problem with Hilton Head is what? Overdevelopment.
Yeah.
And you're going to have change in geomorphology around how Hilton Head is going to be morphed and changed with the next 6 to 11 feet sea level rise over the next 21, over the next 85 years.
Yep.
But the problem is, how do you, I mean, you are doing this for real. How do you get people to shift, not only in the sea turtle world, to understand these ramifications and how we need to peer out beyond over the horizon, beyond the status quo, but also how do you then translate that into directive action in a proactive way to mitigate risk and to create opportunities for these similar species to potentially survive?
Well, I think one way is for us to go around and talk, get more people to come, do more of these talks to people, but you got a small audience, so get on the media, reach out to the media. Obviously, Dave and I should go on the Late Show with Colbert and talk about it. Try and set that up. Get more people to talk about it, get more information out to people, so that people are more aware. Let me show you something. I had a geology colleague who showed me this slide. He said, this melting 380, 400 CO2, he said, well, that was the same level, 380 back, a couple million, 3 million years ago, CO2 level was 380. And sea level was, look how much higher it was. I think it's 20 meters, 35 meters higher than it is now. So obviously it's not CO2. Being a geologist, he should understand the problem of mass. So I showed him this picture, a snowman. You know, the president and Senator Imhoff like to say, well, it's snowing, so there can't be global warming. It's a nice, in my neighborhood, nice little snowman. Snowman family, which one melts first? The little one, right? It's very sad. Well, Greenland's melting. And obviously at 380, there was no ice. That means there was no ice in Greenland and maybe not in Antarctica 3 million years ago. That's why the ocean was higher. It means that the steady state for the ocean at 380 parts per million is no ice. It's just a question of how big a snowman you're talking about. It is inevitable that all of Greenland will melt with the amount of CO2 we already have in the atmosphere. And maybe most of the Antarctic, which means you're going to have 30 meters more seawater. We're all going to be floating. They'll be around. So it's a timeline that we don't know about. So that's part of the issue. But I think people need to realize that we're already at a point where if we don't reverse the situation, then future generations are going to pay that price. Yes?
I had this conversation with another environmentalist about CO2, and it's like you think, let's water the beach to get it cooler. Well, are any scientists working on ways of like canning CO2 or, putting it into something else or create, you know what I mean? Like,
yeah, suck it out of the atmosphere.
Yeah. And
engineers are working on trying to figure that out.
I would think.
It takes a lot of energy though to, like you make helium by taking it out of the atmosphere, helium gas. So maybe you could take the CO2 out and combine it with something to make a solid out of it. I mean, people are working on that. They don't have it solved. It takes tons of energy to do it, so maybe you could use nuclear reactors which don't generate CO2 to give you the power for the machinery to suck it out. Yep, it's certainly possible. So there's a challenge, and I think in general the average person is becoming more aware of the problem, and we're 10 or 20 years behind where we'd like to be on that curve of informing people. But I think it'll become more of an emergency situation in the next 10 to 20 years when everybody kind of realizes, oops, we got a problem. And hopefully this stuff melts slow enough that you could reverse it. If you get it back down to 280 or 350, it'll only take 200 or 300 years to do that. If you stop putting the CO2 in the atmosphere now, then you can reverse that effect.
All right, we're out of time. Thank you very much.
Out of time? I'm just kidding.